Today's lesson is going to be on limiting and excess reactants. As always, I would recommend watching this on either your phone or your computer, so that way you can take notes on your iPad. Before we begin, I want to do a refresher on what we learned yesterday. So, how many moles of oxygen are needed to react with 2 moles of aluminum? To solve for this, we're going to start with our 2 moles of aluminum. And we are going to use our mole to mole ratio to convert from 2 moles of aluminum to our moles of oxygen. And looking at this, you will notice that there are 3 moles of oxygen required for every 4 moles of aluminum used. So we're going to write our 4 moles of aluminum on the bottom per 3 moles of oxygen on top. And when we do this, we are going to get an answer equal to 1.5 moles of oxygen, because our moles of aluminum are going to cancel out and we are left with moles of oxygen. So what this is telling me is that for every 2 moles of aluminum that we use, we are going to use 1.5 moles of oxygen. This means that your correct answer is going to be A. In class, we did an activity that related to s'mores. I would recommend referencing this activity often because it ties into this entire unit. However, in these notes, we will not be doing anything with this slide. We figured out that our excess reactant was the graham cracker piece activity, where we know our ratio of I need 2 graham crackers, 3 chocolate pieces, and 1 marshmallow for every 1 s'more created. So if I have 8 graham cracker pieces, 15 chocolate pieces, and 6 marshmallows, I want to know, well, what's holding me back from making more s'mores? So in order to do this, we are going to start with our 8 graham crackers. And then we are going to figure out that we can create 4 s'mores. We do this by determining, well, if I have 8 graham crackers and there are 2 graham crackers for every 1 s'more, I can create 4 s'mores. We can do this another way. If we start with 15 chocolate pieces, how many s'mores can I create? So we're going to solve for the number of s'mores again, and we're going to see that for every 15 chocolate pieces, for every 3 chocolate pieces, we can create 1 s'more. And so if I have 15 chocolate pieces, I can create 5 s'mores. And then if we have our 6 marshmallows, well, in this case, I have 1 marshmallow for every 1 s'more created, so I could create 6 s'mores, which means that my graham crackers produce the least amount of s'mores, and so that is going to be my limiting reactant, which means that both my chocolate pieces and my marshmallows are my excess reactants. Please notice, s'mores are not a reactant in this case. It is what is producing the s'mores that is going to be a limiter or an excess. In this slide, we're going to be solving for how much excess reactant would we actually use. Since we know that our amount of graham crackers is limiting us, I want to know, well, how many chocolate pieces am I going to use and how many marshmallows am I going to use? So to do this, we start with our 8 graham crackers. So we're going to use up all of our graham crackers because that's limiting us. And I want to know how many chocolate pieces am I going to use. Well, if I have 8 graham cracker pieces, I know in a s'more that I use 2 graham cracker pieces for every 3 chocolate pieces. So that means in order to use up all of my graham cracker pieces, I would need 12 chocolate pieces. Well, we also want to know how many marshmallows am I going to have left over, or how many marshmallows would I have to use. So we're going to convert, in this case, from our reactant of graham crackers to our reactant of marshmallows. And anytime you convert from one reactant to another, that is telling you to use up all of your reactant A, how much reactant B would you need? So in this case, to use up all of my graham crackers, how many marshmallows do I need? Well, I know that in a s'more I need 2 graham cracker pieces for every 1 marshmallow piece. And in this case, that means that to use up my 8 graham crackers, I'm going to use 4 marshmallows. Well, now sometimes I want to know how much would I have left over. So to figure out how much I have left over, I know I had 15 chocolate pieces. I only used 12, so therefore I'm going to have 3 of my chocolate pieces left over. I also know that I began with 6 marshmallows. I only ended up using 4 of them, so therefore my marshmallows are going to be 6 minus 4, and I'm going to have 2 marshmallows left over. This slide just helps to give a good visual representation of how limiting reactants work. So if we pretend that each one of these green dots is a hydrogen atom and each blue dot is an oxygen atom, and here we're mixing hydrogen gas, which is H2, with oxygen gas, which is O2, and I'm going to produce water. Well, in this case, we see on the left side I have 8 total hydrogens and 8 total oxygens. This is the same as me having 4 moles of H2 and 4 moles of O2. So in this case, I'm wondering if I react 4 moles of H2 with 4 moles of O2, how much water, or H2O, can I produce? Well, you'll see that I have 8 hydrogens on the left, and I have 1, 2, 3, 4, 5, 6, 7, 8 on the right. So I used up all of my hydrogen. My oxygen, on the other hand, I have 1, 2, 3, 4, 5, 6, 7, 8 on the left, and I used 4 on the right. Well, since I used up all of my hydrogen, that is going to be my limiting reactant. Since I have oxygen left over, it is in excess and is therefore my excess reactant. So since all of the hydrogen are used in the products and there are leftover O2 in the reactants, and you can fill this in multiple ways, we can say H2 is the limiting and O2 is the excess. Please remember to use this slide whenever you are solving a problem. For example, if we wanted to convert from moles of one substance to moles of another, that would be going from moles of A to moles of B, which would mean we are just using our first step here, which tells us that we want to look at our coefficient of A to our coefficient of B, which, let's say I wanted to go to aluminum, which would mean it is a 3-to-1 ratio, which we see in this step down here. You may also sometimes want to go from grams of A to moles of, say, B, which would be like if we started with grams of lithium and we wanted to convert to moles of aluminum. In that case, we would just follow these 2 steps, which tells us that we need to look at our molar mass of A, which in this case is, and that is always per 1 mole, and in this case our molar mass of A is 6.94 grams of lithium, which comes directly from our periodic table, and that is always per 1 mole. Step 2 is then telling us to do the same thing we did last time, where we looked at our coefficient of A to our coefficient of B. Oftentimes the problem will ask you to solve for, say, from grams of A to grams of B, which in this case would be if we want to solve for, say, a starting amount of lithium to how much aluminum would be produced, where we'd go from grams of substance A to grams of substance B, which is what's being done in this entire example problem down here. So we started with grams of lithium, which was provided to us. And then we're doing step 1, which is our molar mass, like we've already talked about, coming from our periodic table. Our coefficients, which come from the problem above. And we see that step right here. And then last thing, it's just the same as our first step where we take our molar mass coming from the periodic table, which is always some grams per 1 mole. And that is our final step. So here's an example. First thing I always recommend doing is to determine what is your A and what is your B. Well, in this case, if we are going to solve where it says given 0.650 moles of each reactant, determine the limiting reactant and the excess reactant. When doing these, I always just like to convert from one reactant to another. In this case, I'm going to say that we start with our 0.650 moles of Li3PO4, which means that that is going to be our A. And in that case, we're going to solve for our other reactant, which is going to be our B. So if we do that, looking at the last slide, we need to just look at our coefficients of each. So here this is a 2 to 3 ratio. Since I have moles of Li3PO4 or lithium phosphate on top, I would need to put that on bottom, and I have 2 of those for every 3 moles of magnesium sulfate. And what this is telling me is that to use up every last bit of my lithium sulfate, I would need 0.975 moles of magnesium sulfate. Now, realistically, we could already stop here because we know that we need 0.975 moles of magnesium sulfate, and we have 0.650. So what that's telling me is that my magnesium sulfate is going to be my limiter because I have more of it, or I have less of it than I actually need. However, just to double check our work, let's go through and solve from magnesium sulfate in this case. So this time we're actually going to change up what our A and our B are. So we're going to delete those. And now in this case, my A is magnesium sulfate and my B is lithium phosphate. So if we go through and do this, we have 0.65 moles of magnesium sulfate. They follow their same ratios, so it's 3 moles of magnesium sulfate to 2 moles of lithium phosphate. And you'll see that in order to use up all of my magnesium sulfate, I would only need 0.433 moles of lithium phosphate. So therefore, my lithium phosphate is going to be my excess. So if we look at the bottom here, since we need more MgSO4 than we have, it is going to be our limiter. Since this problem is similar to our last one, I'm going to go through this one a little bit quicker. So if we have 2.6 moles of O2 and 0.36 moles of C2H4, what will our excess reagent be and how much will we have left over? So this one does add an additional step where it's asking, well, how much of my excess do I have left over? So let's go through and solve for this. First, let's start off with our O2. So we have 2.6 moles of O2. There is 3 moles of O2 used for every 1 mole of C2H4. So in this case, if we go through and solve for these, we have 3 moles of O2 per 1 mole of C2H4, and we find that we would need 0.87 moles of C2H4. Again, we know that we only have, because the problem is telling us, that we only have 0.36 moles of C2H4. And we've already found out that we need 0.87. So we already know that this is our limiter. But just because we like to do chemistry fun, let's continue on and solve for the next one. So now I'm going to say, okay, well, to use all 0.36 moles of my C2H4, how much of my oxygen do I need? Well, if I start with my 0.36 moles of C2H4, convert, I have 1 mole of C2H4 for every 3 moles of O2, and we see that I would need 1.1 moles of O2. But up top here, we've already determined that I have 2.60 moles of O2. So we can go through and fill this in. Since we need more, in this case it's going to be C2H4 than we have it as our limiter. So to find out how much excess is left over, we take what we have, which is 2.6 moles of O2, minus the 1.1 moles of O2 we needed, because we determined that in order to use up every last bit of the C2H4 that we have, I would only need to use 1.1 moles of O2. Because C2H4 was my limiter, it's what's holding me back, so I only need so much oxygen to react with that, and I would finish with 1.5 moles of O2 left over. Now this problem is a little bit challenging, a little bit more challenging. You'll see in this case we're starting with 25.6 grams of each reactant instead of moles. So we are going to have to do those additional steps if we look back a few slides. So when we start this one off, what we are going to do is we are given 25.6 grams of each reactant. So again, I want to convert from one reactant to another. So in this case, I'm going to start with grams of lithium, and I'm going to convert to grams of aluminum chloride. It really doesn't matter which one you start with, but whatever you start with is always your A, whatever you're converting to is your B. So we have 25.6 grams of lithium, and then our first step tells us to find our molar mass coming from our periodic table, which is 6.94 grams of lithium for every 1 mole of lithium. Our second step tells us to look at our coefficient of A to coefficient of B, which in this case is 3 moles of lithium per 1 mole of aluminum chloride. And then our third step is the same as the first one, where we are looking at our molar mass coming from the periodic table. Again, when I say this, I'm referencing that slide a couple times ago where we go from grams of A to moles of A to moles of B to grams of B. And now our last step, we find out our molar mass of aluminum chloride. And remember, this number comes from the mass of 1 aluminum plus the mass of 3 chlorines, because we have to add all of that together to get us our molar mass. So when we go through and do this, we get an answer. We give us an answer that is equal to 164 grams of aluminum chloride. So again, what that number is telling me is that to use up all 25.6 grams of lithium, I would need 164 grams of aluminum chloride. Well, again, we've already determined that we only have 25.6 grams of each reactant. So right away, I know that I need more aluminum chloride than I have. So I can already go ahead and label my aluminum chloride as my limiter. Or as my limiting reactant, because I need more of it than I have. So now we have to go through and figure out, well, how much of that am I actually going to use? Or how much lithium would I end up using? So this time we're going to go through and we start over, and our A and B now switch. So now my aluminum chloride is what I'm starting with, which is my A, and my lithium is going to be my B. So we have 25.6 grams of aluminum chloride. The molar mass of that, we already figured out from the previous problem, is 133.34 grams of aluminum chloride per 1 mole. There's 1 mole of aluminum chloride per 3 moles of lithium, and for 1 mole of lithium there is 6.94 grams. And please remember, your units should always cancel out. Always go through and double check those. So grams of aluminum, moles of aluminum chloride, moles of aluminum chloride. And sorry, I misspoke back here. Moles of aluminum chloride, moles of aluminum chloride, moles lithium, and we are left with units of grams of lithium. And now when we go through and look at this, we see that we are going to use up only 3.99 grams of lithium. So to use up all of my aluminum chloride over here, I am only going to have to use 3.99 grams of my lithium. So since we need more AlCl3 or aluminum chloride than we have, it is our limiter. Before you watch the tutorial for this slide, I would recommend that you try it out yourself. Think through what you've learned and what the question is asking. So using the provided information from the last slide, how much lithium chloride could be produced? So now we want to know how much lithium chloride could actually be made. Sorry, there should be a little arrow in there. So think about it with your reactants. If one of your reactants is holding you back, that's the one that's going to limit how much lithium chloride you can make. So please pause the video and see if you can solve for this one on your own. Okay, hopefully you've tried this on your own now. But what we need to do is, looking back at the last slide, we had determined that aluminum chloride was our limiter. So basically what that's saying is I don't have enough aluminum chloride to produce all of my lithium chloride. It'd be like if you had only one marshmallow, but then you had 20 pieces of, if you only had one marshmallow, but then you had 20 pieces of graham cracker, well, you can still only produce so many s'mores. This follows the same concept. If I only have so much aluminum chloride, I can only produce so much lithium chloride. So in this case, this is going to be my A, this is going to be my B. So anytime you convert from, say, a reactant to a reactant, that is telling you to use up all of one reactant, how much of the other you would need. Anytime you convert from, say, a reactant to a product, that is saying to use up all of your, if you use up all of your reactant, how much product you could produce. So now if we go through and start solving this one, we're going to start with our limiter because it's what's holding me back. It's called limiter because it's holding me back from producing more of my product. So in this case, I start with my 25.6 grams of aluminum chloride, and we just follow all the same steps. Step 1, we look at our periodic table. So it's that 133.34 grams of aluminum chloride per 1 mole. We look at our mole-to-mole ratio, which in this case, we still have 1 mole of aluminum chloride per 3 moles of lithium chloride. And then our last step, we have to look at 1 mole of lithium chloride per 42.39 grams of lithium. And I apologize, this is typo on here. This should say lithium chloride right there. And then we go through, we find our final answer, and we see that we have, where we are able to produce 24.4 grams of lithium chloride. So again, what this number is telling me is that if I use up all of the aluminum chloride that I have in my cupboard, I can produce a maximum of 24.4 grams of lithium chloride. So now what we might want to know is, now that I've used up all my aluminum chloride, how much of my other reactant, my lithium, am I going to have left over? So to solve for this is actually pretty simple. On the last slide, we determined that to react with my 25.6 grams of aluminum chloride, I would need 3.99 grams of lithium. And the last problem also told us that we were starting with 25.6 grams of both reactants, which means I had 25.6 grams of lithium, and I also have 25.6 grams of aluminum chloride. But to produce this lithium chloride over here, I used 25.6 grams of aluminum chloride, and I used 3.99 grams of lithium. So that means if I want to know how much lithium I have left over, I just have to take my grams of lithium that I have minus how much I needed, and we will get an answer equal to 21.7 grams of lithium left over.